All right, my friends, welcome back to Build Science
201.
All right, guys, our last module on vapor. What are we talking about today, Steve?
We are talking about, well, it's a rate question.
Is it too much? Is it too little? Is it wet or is it dry? We got a great episode, guys. Let's get going.
Build Science 201 is sponsored by Andersen Windows and Doors, Huber Engineered Woods, and Proseco.
Hi everyone, I'm Matt Reisinger, and today I want to talk to you about a brand that has a remarkable 120-year legacy in producing quality, performance-focused products. That's Andersen Windows. In the South, especially here in Texas, that legacy really comes to life with the Andersen 100 series. Gosh, I think I started using this line when it very first came out, and from the beginning, I have really liked this window. This line enables you to choose dark colors without sacrificing performance. That's right, style that doesn't compromise on quality. One of the key features of the 100 series is Fibrex, Andersen's proprietary material. It's actually 2 times stronger than vinyl, which means you won't experience flex over time. Your weather stripping stays tight, and that's going to ensure that both air and water performance, water holdout that is, remain top notch. Now let's talk about performance enhancements. Andersen is expanding their triple pane offerings, which is a fantastic option for energy efficiency. You can find triple pane windows available in the A series, a FIAS certified E series, and now even in the 400 series at select locations. So whether you're looking for style, strength, or energy efficiency, Andersen has you covered. With a commitment to performance that you can trust that these windows are going to stand the test of time. Thanks for joining me today, and if you're considering new windows for your home, definitely check out Andersen and see the difference for yourself. All right, Steve, talking about vapor, and specifically on this module, we're talking about rate. What do we need to know?
Rate. Well, we're talking drying potential and wetting potential. One needs a lot more time than the other. It's okay if things get wet, as long as we can let them dry.
That's right. If it can't dry, it's gonna die, my friend David Nicastro says.
There you go. So, one of my favorite pictures, how did we dry wood, right? So this is a job site where we had some trees. We had a guy come in with his portable sawmill, cutting it, but look what's happening here. All of these slabs are on sticks, simply drying.
Yep, that's how we've done it for many, many generations, right?
Yep.
Cut that log up, put it up so it's got some airflow, and let it dry.
Yeah, it's amazing that as we progress in the building industry, we forget some of the very simple things that we used to do.
Yeah, for sure. How does that translate to a modern house? I have an example for you. So Steve, this is a 1915 house, roughly. Pretty old for Austin, Texas. We don't have a whole lot of houses much older than that. But we came to do a remodel on it, and I knew this was a wood framed house with wood siding, and I assumed wood shiplap probably behind that for sheathing. But one interesting thing, Steve, is we found some old photos in the house.
Right. Now, one of the things before we jump to that, let's take a look at this photo. A couple things to learn from it, right? We have a vent there.
Yep, vented crawl space.
And we have a vent there.
Vented attic.
Back then, over 100 years ago, they knew the idea of wetting and drying. Now, what they didn't have was a way to measure whether or not things were drying or staying wet, etc., whether or not that attic ventilation was enough, because there is no real ridge vent.
That's right.
Along there. So they had the concept, they understood it, but now we have the measurement tools, but we avoid the concept a lot.
True.
So it's really interesting that through time, how that switch happens.
These old houses teach us a lot. And this is an interesting photo. So I mentioned that we found some old photos. I suspect this was taken in the 1960s, maybe. The house, when it was built, obviously never had any air conditioning in the house. It had some radiators for heat in the wintertime, and that was it. But they added some what I call window rattlers, a unit that sits in the window and air conditions. And what I loved about this photo, or I thought was interesting about this photo rather, look at the staining on the wallpaper. Yeah. Now, it turns out this house never had sheetrock when it was originally built, or no lath and plaster either. Behind that wallpaper was shiplap, was basically 1x boards that they put muslin on top of it, and then they used wallpaper on top of that. So that's the finished wall. And so seeing all that staining on there in this old photo, I thought, oh, this is going to be really fun to take this house apart, because I suspect we're going to find all kinds of mold and problems on the sheetrock that was added around that same time period, I would guess, 30, 40 years ago. Now, pop to the next slide and we'll look at demo. So now that we've demoed the sheetrock that was there, and the wallpaper came off behind that as well, that's the original shiplap on the inside. The outside was sheathed with the same thing. And you can kind of see at the bottom of that wall there, 2x4 framing and an uninsulated cavity, except for some bays that they could insulate from the top of the attic. So they did actually insulate a few bays. But as I was looking around, especially at those windows that I was expecting to see from some leakage, some problems, zero issues.
Dry as a bone.
Dry as a bone. And also no issues on the back of that sheetrock either, which I thought was really interesting. So as we're talking about vapor and rate, that wetting versus drying, what's happening, I think, in this house all those decades was that when the house got wet, it was allowed to dry. There was hardly anything that was stopping the air from flowing through these walls. It made the house probably not super comfortable. I bet it was really hot in the summertime. It was probably pretty cold in the wintertime. But you know what? It lasted a long, long time. I mean, when we remodeled this, it was just shy of 100 years old, and it was still in fantastic shape. So what are the takeaways from that? Can we do this today? Yes and no, right? We can't build a house without insulation. We wouldn't want to. My customers would never put up with an uncomfortably hot house in the summertime or an uncomfortably cold house in the wintertime. And codes wouldn't allow me anyways, even if I wanted to. But what we can learn from that is when we build with wood, we need to be cautious about the rate of wetting versus the rate of drying.
Yeah, and one of the things you'd mentioned it there, the rate through that wall is very, very high, right? And it saves a lot of those kind of pre-World War II homes.
Yep.
The fact that it's not insulated, we can't do that. The idea that the minute I add insulation, what I do is I slow the amount of energy that can move through there. The intensity as well as the rate and the migration of that heat loss through that wall system, or vice versa down south. But the limited amount of energy there makes the wall a lot less forgiving.
Yep.
And I'm guessing on this house, that wallpaper probably slowed a bunch of moisture going into the wall.
Probably.
Which helped on the wetting potential, as well as it was probably just a really bad air barrier, but it probably helped in a sense to keep wind from blowing through.
But that's right. Yeah, it probably did a good job or a decent job of a wind barrier on the inside too.
Well, let's talk about when vapor goes bad. Yeah, this roof, again, wetting, drying potential. That's just signs of things getting wet, staying wet. Remember, mold, if you remember, 3 things: the right temperature, water activity, and a food source, right? Hot roof, cellulose-based, and we get a little bit of moisture build up in there because the venting isn't properly done.
Yep.
Yeah, so on this one here, this is a photo that we talked about from other perspectives, but in terms of wetting versus drying, this is really enhancing the drying of that roof now. So we get rid of that mold problem by just really driving that air through the top of this roof system.
Yep.
And if you're in new construction and you're looking to do it right, to battle wind washing, we like to foam in our baffles. So this is a vented roof system. We're just making sure that the vents are put in a position for success.
Yeah.
Right. And even in complex roofs, this is the hip section of that roof. Notice that we go up, we're well above our insulation level, which is probably somewhere in there. I like to go probably about 16 inches past the top of the insulation.
And I think it's worth noting, what is the spray? The spray foam's coming above the top plate and onto those baffles. What's the purpose of that, Steve?
Yeah, coming on there is so that we don't get wind washing, right? Any air that's coming in through that soffit vent, we don't want it to go sideways into our insulation. And I know you have seen it where it actually blows the insulation. And so the insulation will then look like this.
Yeah, my old house had that.
Right, so it'll blow this up.
I had to fix that on my 70s built house because they didn't have any of those baffles in, and all my soffits washed away, such that you'd go up in the attic and you'd see bare sheetrock for the first 8 inches a foot, which meant I was absolutely gaining so much heat, and that space of my ceiling right there was crazy.
Yeah, so the takeaway here is that if you're putting in a ventilation system, you have to make sure that that ventilation system is put in a position to succeed.
Yep.
You know, and this is a SIPS roof. The SIPS actually stops here, and then we have an extended rafter tail on the roof system. But because it's a SIPS problem, or a SIPS roof, I didn't want to have the problem of moisture migrating through it, but then getting stalled at a barrier here, right?
Smart.
There's a lot of guys that'll do SIPS roofs and, oh, we got to make sure that we don't let any water in there. We'll fill up the whole roof with ice and water shield, right? And so the issue there is eliminate the idea of putting the ice and water shield because it doesn't allow any drying across it, but introduce an airspace now that we could take that air from the soffit up into a space over the SIPS roof and let that run up the roof.
Yep. That's really good.
Wall systems, right? There's probably no better drying potential than an open joint rain screen. And, you know, we get a lot of people that come and talk to us and say, oh, but you're letting all this water in. Because, yes, all of these joints, those are a 3/16 inch joint, and they are wide open. Water can get in. And I know what you're thinking. Oh, well, imagine all the bugs that are going to make that a home. It's not a place that they love. I have a dozen of these houses, open joint rain screen. We had one bee viewing by
And that's
one
it.
client.
That's not bad at all.
That's it. We've
That's crazy.
never had a problem with it. They don't like it. And, you know, I'm going to credit that to Joe because working with him, when we talked about rain screen systems and stuff and people talked about bugs, he's like, no, it's a place. It's not moist. It's not a place that they want to live.
It's not conducive.
It's fully vented. It's dry. They won't live there.
Yeah. One of my favorite quotes that I think is apropos for this is, it's not about keeping water out, it's about letting water out. Another David Nicastro quote. And that makes a lot of sense to me when I look at this image right here. I suspect there was no caulking between that window frame and the window itself.
No, there's actually the same 3/16 inch joint ran all the way around the window.
And you could caulk that if you wanted to for aesthetics, but why do it? Because if you caulk it, you're going to have to re-caulk it. So let that water out. Don't keep it out. Make a path for that water to get out of the assembly. And back to this vapor drive question too, or what we're talking about here for vapor in particular, is that wall assembly in a cold climate too means that you're going to be able to drive through that assembly into that ventilated space. And so this is a safer wall all the way around for your cladding and for the wall behind it.
Yeah. The air can go in, go up. We'll vent it at the top there. We have a vented roof assembly there. And it doesn't need to be vented at the top actually because it's vented the whole way up the wall.
Yeah, that's right. Because this is an open
But if you did that
joint.
as a closed system, then you would just have to put that vent at the top.
That's right. And don't forget that vent at the top. That's really important.
One of my favorite houses, we just finished this one, the Riverside house. So you were there. We shot a bunch
Beautiful
of videos.
house.
Bunch of open joint rain screens. So this is very similar to the previous slide, except the orientation of the joint work now is vertical. But the concept is exactly the same.
It's pretty.
I can let a little water in and let it out. Now, those of you that let water in, I've done a lot of water testing. The thing about water is that if I took this, find a section here, and let's say I sprayed a whole bunch of water on that wall, what's going to happen is that wall, the water is going to go, it's going to find the edge, and it's going to ride that edge to gravity. It's going to take a lot to push that water in because there's not much of a pressure difference. When the wind blows on this wall, the air can go in here, but it can come out here, right? So there's not really that driving pressure. I know we don't use that term anymore, but it is pretty much a pressurized, an equalized, pressure equalized rain screen, right?
That's right?
So it's really not playing to the forces of a leak.
That's smart.
While we show a whole house, it comes down to details too. So this is just a mock-up. we had a full plywood corner here so that we can grab the siding here on both sides. But we have that plywood corner, so what we did was made sure we had a space through here, and all the builder did was take some cutoffs and added them to that to get that space. And now we have drying potential behind. This is all, raw cedar. It's obviously going to get treated on the outside, but it has the ability to breathe.
That's a great detail.
Wall system. Getting back to houses need to breathe. Yes, they do. And this is our breathing apparatus.
That's the lungs for the house.
Right? This is our scuba gear for the house, right? So all of this ventilation, well, this makes sure that if we do have moist air in the house, say bathrooms, kitchen, any generated moist air, then we're evacuating it. We're bringing in new outside air. We're exchanging the energy in the ERV and dumping that back into the house. And this is another photo of distribution of that system. Notice this is a slab on grade house here. And with slab on grades, you don't have the ability to say, hey, we're just going to go in the basement and we can solve for all of our HVAC. No, we had to solve for that above the slab. And when you're running, I don't know, we're probably on the order of about 250 linear feet of 3-inch hose. And this is only a 1,500 square foot house.
Dang.
But it's the distribution that makes this system effective, right? Going to every room, pulling from each of the bathrooms, and then redistributing it. That redistributed moisture balances out across the house, and it kind of evens that wetting drying potential scale.
Yeah, that's good.
And sometimes in a house, this is the outlet for that ventilation system. We had a client that said, can we put those somewhere where I don't want to see them? I don't want cold air blowing on me in the summer. So in the bedrooms, we had solid doors to the entry, and then we had louvered doors where air could pass through on all the closets, and we put all the vents in the closet, which is actually a pretty cool idea, because one of the places when we used to do building investigations and we were looking for problems, we'd go into the closet and we'd grab a cardboard shoebox.
Oh, interesting.
And we'd look for mold on it.
Huh.
Because that's stale air. That's air that's not usually getting exchanged very well. The cardboard is a great food source. The temperature in there is usually a little different than the room when I close.
A little colder, potentially.
A little colder. And so there's a really great potential to grow mold on that shoebox. So this actually really helps solve that problem and dumps the air into the closet and pushes that air out so the house is breathing even better.
That's great.
And then, of course, outside, wetting versus drying. So this is a house. You can see there's a concrete slab right here. And notice the sheathing is in the same plane as the concrete slab. They actually had to chisel it here because it was out in front and created a little shelf. But they had to cut that back. But the moral of this story, and actually I knew it would be higher. I didn't realize it was going to be this high. Good friend Peter Yost and myself, 18.1 down at the bottom of the wall. We went up the wall 3 feet, and we're at 8.9%
Holy
moisture
cow.
content.
Big change.
This is 2x in 3 feet, right? So when you're talking about wetting and drying potential, having a rain screen on this, yeah, maybe it doesn't matter that much up here. But that rain screen means everything to the success of the wall down here.
That's right.
Because you're closing in on that 19%, which is,
that's really high.
You should be lower than that for framing lumber.
Yeah, I would say you need to be below 15% before closing.
Yeah. So
that's really good.
But this is the detail where, because it's in the plane, you get water coming down, it turns the corner and then goes right back up and sucks up capillarity.
Yeah. As a side note, Steve, when I was working in a very rainy climate in Portland, Oregon, 40 inches annual rainfall, we'd get rainy pretty much days and days and weeks in a row in the wintertime. We'd be framing during that whole time. We made sure that before we moved on to hang the drywall and moved on to the next stage of construction, that we would use a moisture meter just like that and check all our bottom plates, check our studs a foot or so up around the house, so we could make sure that we were at a lower percentage, because we didn't want to close the house in and cause an issue with trapping something in those areas, trapping moisture in those areas that couldn't necessarily dry as easily once the drywall was up, once the vapor retarder was up, those kinds of things. So we always made sure that our houses were below 15% at every location, every reading, before we moved on to that next stage of construction.
Yeah. And you know, this, if we went back to your 1915 house there that we first showed and we circled back, this probably wouldn't be that big of a problem, because we have that energy drive across that wall system.
That's right.
So if things got wet, we could dry it out.
Yep.
But we don't have that anymore.
No, it's
right?
gone.
This is getting a whole bunch of insulation. It's probably getting some drywall and a membrane on the inside. That energy drive has been really lowered.
Good stuff. Okay, guys, stay tuned to our last control layer. We've got 3 more videos in this Build Science 201 series. We're going to be talking about thermal control. With that being said, we'll see you next time on the Build Show.
Sponsored by Anderson Windows and Doors, Huber Engineered Woods, and Proseco. This is Build Science 201.